Hi guys, I'm Raechel.
And I'm Omar.
And our research project, as you can see, is on analyzing amateur astronomy tools for their use in exoplanet transit observation. And I don't know if you guys are excited, but I am very excited. All right. So let's talk about exoplanets for a minute. So exoplanets, or as they're more technically known, extrasolar planets, are basically just planets that orbit another star, any planet that does not orbit the sun. And that doesn't seem like a big deal, but it's actually a pretty big deal because right now we have, this is a little out of date, 879. It's more around 900 right now, but that's confirmed exoplanets through multiple observation. And we have about 3,000 exoplanets that are unconfirmed. Now, this is important because about 10 years ago, we had 0 confirmed exoplanets. So people didn't even know if they existed about 20 years ago. So this is pretty big. This field has explosive growth. It is ridiculous. The amount of planets we are finding every day is just an immense amount of data, and it's a really lucrative field right now, and actually one of the newer fields of astronomy.
Well, there are several detection methods to detect these planets. And the one we used for this research project in specific was the transit method. And the transit method is when you take pictures of the star when the planet is in transit, when the planet is in front of the star from our view here at Earth. You take a picture of it, you calculate the magnitude of it, and then you do the same thing for when the planet is not in transit, so when it's just the star by itself. And then there are several other ones: radial velocity, astrometry imaging, direct imaging, and gravitational microlensing. And radial velocity is just observing the different wavelengths and how they change when the exoplanet is around the star. And usually there's quite a big of a difference when you do this types of observation. There's the astrometry imaging, that's the observing the star, and its position changes, and that's almost a little bit of the wobble of the star because of the gravitational pulling of the planet. And then the direct imaging is when you take direct images of what's around the star and see if you find anything. And then the gravitational microlensing is detecting the light being distorted, like we saw when we went to the dark matter stuff. It's pretty awesome.
All right, so we're going to talk about CCDs and their part in astronomy. So CCDs are actually really important to astronomy right now. They pretty much revolutionized the field of astronomy in being able to take higher quality images. And basically, a CCD is a charge-coupled device, and what it is a camera that collects photons on the light-sensitive pixel surface. In the case of astronomy, it's usually made of silicon, and it turns those photons into an electronic signal that are turned into an image. This is the exact way your cell phone camera works. So these CCDs are everywhere, but they're especially important in astronomy because they have a quality known as low noise. And what noise is the interference of background electrons on the electronic signals that are turned into images. Previous methods before CCDs had a lot of background noise, and you wouldn't get as crisp or high quality of an image. And so it is very important that we have these because they make pretty good images. And the most important part of our research is that they're very easy to access and very easy to use. Most modern day telescopes will have a CCD.
Also, what makes a CCD is very, very special is its quantum efficiency. The quantum efficiency just talks about how many of the photons it actually captures and stores. So today, with modern technology, a CCD will capture from 90 to 95% of the photons that it's received and put them into the output, which is the image. The image makes it very accurate because you get most of the photons, they're all put into it. And also it's very precise because of the low noise, so you get very precise data on what exactly you're observing. So in exoplanet observation, precision and accuracy are so important because you're dealing with such small numbers. For example, like the magnitude changes that we're going to see here in a little bit in our results, the changes are so tiny that you would need very precise measurements to be able to see the difference. Okay, so amateurs and professionals. So let me start off by reading this quote to you. Amateurs provide scientifically valuable and critically important information to multiple fields. Bruce Gary said this. He's a very accomplished amateur astronomer. He pretty much wrote the book that we use on our whole research. He observes and he helped us. Well, he didn't really help us. His book helped us to find different detection methods that were the best in whatever we were doing. So that book very much helped. And the reason that amateur astronomers are so important to this field is because there's so much data that comes in every day from observing exoplanets to observing nebulae to observing other galaxies. There's so much data that comes in that amateur astronomers are really needed to lighten the load on professional astronomers, so they don't have to be like constantly, going through things and using all these telescopes that are like in constant use, and it lightens the load on their back.
Yeah, those telescopes, the big ones in space, they have really long waiting lists, so you can't observe a star for too long. Otherwise, the people on the waiting list are going to get mad at you. So amateurs can really help because they can point their telescope wherever they want. They're the only one in line for it. So, all right, so let's talk about what we actually did for our study. So basically, our question was to see, can amateurs do what professionals do? Can amateurs detect and observe exoplanets with the equipment available to them, the software available to them, and the best method for their resources? So we mainly looked at equipment, and the three factors of the equipment are the effectiveness. So what quality telescopes can they use? What can they get their hands on? Is it an old beat-up Navigator from the 70s, or is it the highest, the brand new hot telescope on the market? Yes, there is a telescope market. And cost. Cost is a big thing. I don't know about you, but I definitely couldn't afford to buy a $10,000 telescope. And so we definitely need to look at that. And location. This is especially important because professional astronomers have access to big observatories all around the world. And those observatories are probably pretty far away from any major city. However, an amateur astronomer might just have an old beat-up telescope in their suburban backyard and be subject to light pollution and other problems that professionals might not have to deal with. So we definitely looked into location. And methods. Which method would be the simplest for amateurs to use? That turned out to be the transit method. And so, as it states up here, we wanted to ascertain whether or not equipment available to amateur astronomers allows for amateur detection and observation of extrasolar planets.
Okay, so the planet that we used was, or the star actually, that we used was called Trace 3, and its exoplanet was Trace 3b. Go figure. The planet is around a Jupiter size. It's slightly bigger, as you can see from the picture down here. It's very close in proximity to its host star. Its orbital period is around 1.3 Earth days, so around 31 hours. So every 31 hours we could observe a transit, but the transits don't always happen, at the right time. So if it happens in the middle of the day, you can't observe anything unless you want to lose your eyeballs or something. The drop in magnitude or brightness, and magnitude and brightness are totally different. We will talk about that. Is 3%, and that's an acceptable statistical evidence for Trace 3.
Okay, so in order to ascertain the proper materials for an amateur astronomer, the system we used was called the iTelescope system. It used to be called GRASS, or Global Rental Scope, because that's what it is. It is a global telescope rental system. They have bases in New Mexico and Arizona and Spain. And we picked the Spain base first because it fits the best sky view for imaging Trace 3. New Mexico was our backup. We very quickly learned that New Mexico was not a viable option as it is monsoon season. And it rained out every single observation. So New Mexico didn't work out. Spain, however, did work out. And the telescope right there, as you can see, the IT-7, it's a deep space astrocamp observatory. It has a CCD on the back. Those are all those wires. And we found some problems with the telescope system. The weather, obviously. Don't get me started on the weather. Oh, boy. The weather, as you can tell, it was a pretty big setback. We had a lot of weather issues. But that is not inherent to the iTelescope system. What is inherent to the iTelescope system is technological problems. We had a couple instances of data loss, and it wasn't significant data loss. We probably lost about 5 images total. But what was significant was a massive computer shutdown that locked us out of the observatory for 24 hours when we were due to observe two transits, and it was very bad. So that is inherent to the telescope system, but it is without a doubt the best system available for amateur astronomers at the present.
So as she was mentioning, that's the telescope we use, and that is the interface for iTelescope. It's very easy to navigate. There is, right there is New Mexico and all the telescopes that are there, and then there's Spain and all the telescopes that are there, and we use T7, which is the first one. And then there's the ones in the Southern Hemisphere, which is mostly located in Australia. They were thinking about adding some more somewhere else. And they were actually thinking about adding some more in California, which would be awesome. It would actually help with the whole weather issue. And the other materials that we used on top of iTelescope was VPHOT. VPHOT is a sub-website of AVSO. AVSO is the American Association of Variable Star Observers. They use this website allows you to upload pictures that you've taken, and the computer system of VPHOT analyzes these photos for you and gives you comp stars. And comp stars are comparison stars, whose magnitudes we use to compare and find the magnitude of whatever object we're observing, in this case, trace 3. And image stacking is very important in this process, because you literally stack the images on top of one another and take an average of all the pictures to find the average magnitude of the star for each observation.
So the methods that were utilized to find the view times for non-transits, or the ideal view time, we had to take into account, we had to take into account the view times for non-transits, and we had to take into account the air mass, which is the amount of air between the telescope and space, and we wanted it to be as close to 1 as possible, so we used the almanac to find that. And then to find the times for the transits, because they don't just happen every day, we used the Exoplanet transit database, and that helped us to find what times we needed to observe and for how long. We would reserve the appropriate telescope, which was interesting in and of itself. There's a very long reservation line. And then the transits we collected were on June 26th and July 19th. The non-transits were collected on the 28th of June and July 8th. We imaged the star through a V filter, which means it collected light 500 to 600 nanometers long. And we imaged it for 180-second intervals, and that's how long the telescope was exposed to space. We would take multiple images over a 33-minute span, which allowed us to factor out any problems if a satellite went overhead, things like that. And we would transfer it to VPHOT, analyze, and graph the data.
Well, this is one of the pictures we took of Trace 3. Trace 3 is the star that's right in the middle, that big one. This is just one of the pictures so you guys can get a visual of what they look like. We we invert the picture so it's easier for VPHOT to be able to analyze it.
All right, so the data we collected, the typical magnitudes, we got 12.376 and 12.377 magnitudes. The transit magnitudes are 12.394 and 12.395, which is very good. However, it doesn't look good. It looks like the star got brighter. But the thing about it is, when magnitudes rise, brightness drops. That's why magnitude and brightness are not the same thing. Can you write the equation on the board? We actually have to run them through a conversion equation. But when we did that, we calculated a 2.6 drop in brightness. That is really good, because the generally accepted brightness is 3%. So we came very close. Amateur equipment was able to precisely and accurately detect Trace 3B's transit. And just real fast, you can see the graph of our data, where the 100% magnitude line is at the top near those 2 dots, and the 98% line is down near the bottom. And so this means that amateurs can indeed assist professional astronomers in detecting and observing extrasolar planets. Limitations faced by both are very much the same, like weather and moonlight, but amateur astronomers do face technological issues, and this means that we can expand the field of exoplanet research in the future. And we'd like to acknowledge our sponsors, the FSI staff, Lori Ball, and everybody who made this possible, particularly Dr. Dietz, who couldn't be here. He's climbing mountains. So we'd like to thank all of them for their help. Thank you.